Hi, I'm Ben-Yaakov. This presentation is entitled Flat Magnetics for Switch Mode Converters, a Primer. Please note that this is an educational tutorial and it is not meant as an engineering design guide. Also, tables and images and other material which is copied from datasheets of commercial companies are for illustrative purposes only, and they do not imply endorsement or recommendation of any product. Also, be aware that I am not affiliated with any ferrite core manufacturer or transformer vendor. There are sort of two types of cores. One is shown here on the left. This is just an ETD core, this geometry, while we have the flat magnetics or planar magnetics, which is shown here on the right, intended primarily for printed circuit wiring rather than copper wires wound around the core. And the question is, of course, what's the difference between these two and what's the benefit of using one over the other, and in particular, what are the advantages of the planar transformer or flat magnetics over the conventional older E-cores or any other shape of core. This is a pot core, for example. Now, the planar magnetics is structured as a core, a flat core. Here there are the two halves of a flat core, and then there are in between the wires, which could be on a printed circuit board, some insulation in between. This would be the secondary, and then we'll have the primary, and then again the secondary, and there are some insulation in between, and then all are clamped together. Also, we see here in this particular case, actually sort of a cover which is serving also as a heatsink, and this can be attached in fact to a heatsink to transfer the heat generated within the core outside. Now, the plates themselves could be printed circuits or the so-called lead frame. These are actually flat copper. This will be for, of course, heavy current. They are thin, so the skin effect does not affect that much the RA. So the question is, what are the benefits of the flat magnetic structure? Well, the first one is, of course, the convenience, the fact that the wiring could be on a PCB board so that the cores are clamped around the board, and this is very convenient. Of course, you don't have to have a bobbin, you don't have to do the winding of a copper wire. Another advantage is the fact that the design is such that the window area for the winding is much smaller than a conventional core, and of course, assuming that these two will operate correctly at the power level designed for. And if this winding area is smaller, this means that there will be a lower number of wires or copper conductors, and therefore the copper loss will be lower. Also, since the thickness here is less than here, say, then the heat conduction is better, so therefore you can actually use a heavier current in the conductor. And finally, since the structure is smaller, you don't have a buildup of the magnetic field, and therefore the proximity effect losses are expected to be lower. Another benefit of this structure is that the leakage will be smaller in a transformer between the primary and secondary or a coupled inductor, and that is because the distance between the primary and secondary is smaller. Now, the leakage is a function of the distance between, say, primary and secondary, and the volume here encased within the windings. So therefore, if the structure is small as compared to this, the leakage will be lower, and this is one of the important advantages of the flat magnetic or planar magnetic structure. Another issue that I've already referred to is the better heat conduction because of the size, because of the geometry, and therefore you can allow a higher heat dissipation within the core and in fact also in the conductors. Of course, this means higher losses, but sometimes you'd like to operate the core at the maximum power possible for a given size. So if you can increase the dissipation without increasing the temperature much, this could be an advantage. And finally, of course, the issue of low profile. And of course, the question is how you put a conventional transformer, whether it's standing up like vertically or horizontally. Even so, flat magnetics will usually be of a lower profile than the conventional core. And now to the disadvantages. We have higher interwinding capacitance. This is because we have flat areas here and the distances are smaller. So the flat magnetic transformer will tend to have a much higher interwinding capacitance between the primary and secondary, or any two windings. And there's a poor utilization of the window area because if you are going to use PCB, then obviously you're not filling up this winding area with copper. There's a lot of PCB material in between, and therefore the area that you are actually utilizing is much smaller. This would mean that you need a larger area product, and I'll talk about it a little bit later. And finally, the footprint would be larger than the conventional transformer when standing up. Now there are other issues that I'm not discussing. This is a primer, it's an introduction to the subject, all the thermal issue, the temperature rise, etc. Question of EMI, emission, shielding against radiation from the gap in case of a inductor, a coupled inductor, and also of course a safety issue, insulation between primary, secondary, and to the body. And all these are to be of course considered when an engineering design of a magnetic element is carried out. Now the example I'm going to look at is for application in which there is a need for a coupled inductor. For example, in the flyback we have this element. This is a coupled inductor. There's a primary, secondary, and these two are inductors. There is an air gap or a distributed gap in this structure in order to allow energy storage within the element. Another example will be an element for a resonant LLC converter. Again, this is a two or more windings. Then we usually incorporate this additional resonant inductor within this coupled element, so therefore it's actually a coupled inductor rather than a transformer. Let me start off with the basics of magnetics in order to come up with a design procedure that we can follow in order to design an element like a coupled inductor. So I'm starting with this relationship. V is equal to N dphi dt. Phi is the magnetic flux of within the core, and then of course we can take out the area. The area is the area, cross-section area of the core. So we have NA, the area, dB dt. B is the magnetic flux density. Let me just say that I'm working in the MKS, so SI unit, which means that phi, the flux, will be in Weber, V in voltages, B in Tesla, the Weber per meter square. And in many data sheets you'll find Gauss, which is related to Tesla. 1 Tesla is 10,000 Gauss. So the first thing we can do, we can ask what is the relationship between this area, cross-section area, and B max that we allow. The question is, what is this value? Is going to be discussed later on. So I'm just assuming that there is a limit here that I like not to pass. That is, this will be the maximum value I want. So I start with, again, these two equations. V, this is the state space equation of an inductor. V, N dphi dt. These are equated. And now I'm actually taking the integral from 0 to this point, okay? And therefore I'm reaching a certain B max here, and also a certain I max here from this the IDT, taking the integral. So this is the I peak times L equal to NA is the cross-section area, B max, from which I can get this expression. So this expression relates the area needed, cross area needed, for these parameters, for the L, I peak, N, and B max. I can also use this equation later on, we'll see it, to calculate the number of turns that I need if I know all these already. So this is the cross-section area which is determined by the B max that I allow. Another consideration is the winding area. I like to fill it up with wires, copper you might say, as much as I can in order to utilize the core to optimum. So we calculate here the area needed for a given application. We start with the definition of the current density in a wire, which is the IRMS over the cross-section of the wire. This is the wire, okay, the cross-section. Or the cross-section required for a given case is the IRMS over J. Now the total area within this window required for a given winding is the number of wires, number of turns, times the cross-section area of the wire, divided by K. Now what is K? K is the filling factor. It takes into account the fact that we cannot fill out this area with copper. There are voids here, and it depending on the type of the way we wind it, insulation, and also of course in PCB there's some areas here which are taken by the PCB itself. So K is a number smaller than 1, and we'll talk about the range that is practical. So therefore, since I know the expression for the cross-section area that is needed, I can find out that the area needed for a given winding is the number of turns times the RMS through these wires divided by J, and K the filling factor. So the total area that I need for all the windings is of course the sum of these areas for each one of the windings. Now, taking this into account and the fact that this area is equal to this term, I can take out N1 out of the summation here and JK out of the summation here, and I get this expression. What it says is the winding area is equal to N1 winding, number of turns of the first winding, J over K. I assume that it's the same for all the windings. And the sum of Ni for a given winding, is from I actually 1 to N, whatever number of windings we have, divided by N1 times the IRMS of a given winding. So this is the total area that I need. And then I have already the area of the core, and when multiplying these two together, by the way, you see that when multiply, should be N sub 1, this drops out, and we find that the area product, this is this term, this is the definition of this term, which is the cross-section area of the core times the area of the winding area, is equal to this expression. This is the most important equation for designing a magnetic element. In this case, we are talking about a inductor or coupled inductor. So how do we calculate the value here for a given application? Well, the value of L, I peak, and I, and 1, all the number of turns, as well as IRMS, or this ratio, and IRMS for each winding, is given from the electronic design. That is, when I design the circuit design, I'll get these numbers. I have to decide what should be the values of B max, J, and K in order to calculate this. Now, the consideration here is primarily power loss, or temperature rise, you might say. There is an experimental equation here. It's a experimentally fitted equation. Actually, it's for E-cores, which shows the relationship between the temperature rise in the core, so the so-called the hot spot temperature, as a function of the total power loss, this is with the core loss and copper loss, divided by the total surface area of this element, and then to the power of 0.833. Again, it's a experimentally fitted equation, which sort of gives us an indication of the temperature rise that would be expected. It's the first iteration, you might say. So we have to choose these so as to keep the power loss at a given level, at a safe level, such that the temperature will not go up too high. Now the J, of course, there's a question of efficiency, and if efficiency is of prime importance, also I'll choose these so as that the total loss of the core will be as one would like to have. Now, a number, which is a sort of rule of thumb for J, has been around for a long time, something like 4.5 amp per millimeter square. Now, we are working in MKS, which means that we have to have it in meters square, so it comes out to be 4.5, 10 to the 6th amp per meter square. Now, this is for a conventional structure transformer. For flat magnetics, since the size is smaller and heat conduction is much better, you can probably go up to maybe 7 to 9 even, depending on the structure, depending on the thickness of the window. So this would be the numbers that you might use. Eventually, you'll calculate the total resistance of the wire, knowing the RMS current. You can calculate the power loss, and then iterate if it turns out the resistance is too high or maybe too low, that having a transformer with too low losses is a waste, actually. So this will be for the J. Now, what about the K? K really is tricky because it's a question, how well do you fill the winding area? Now, if it is wires, fine wires, and not much insulation between the windings, you can go maybe up to 0.8. But in flat magnetics, again, because you have PC boards, etc., this number could be fairly low, something like 0.2, 0.3, etc. So these are these two numbers. Now, what about B? So let's have a look, first of all, at the properties of power loss of a ferrite material. Now, a good point to begin at is this chart here. Now, this chart shows, they call it F times B max. Well, this is not a very good expression. I would rather have it switching frequencies times B hat, and or B peak, and I'll explain the difference in a second. So this curve actually shows different materials. These are 3696, the 3F5, and some other material, and shows this figure of merit. Okay, now what is the meaning of this figure of merit? I'll talk about it in a minute, but before that, let me try to explain the confusion here and to sort out this issue of B max, B hat, B peak, etc. Now, the way vendors, manufacturers of ferrite are measuring losses in ferrite is by exposing the ferrite of the core to a sinusoidal excitation with no DC. In this case, B max and B hat, this is the amplitude here, is the same. No question about that. In practical application, say in inductor, you may have DC. So B max is this value, but the amplitude of the excitation or the perturbation is different. This is this B hat or B peak, you might call it. Okay? Now, what is responsible for losses is this, the ripple. So here we have the ripple. In case of a triangular, actually, again, our information is given for sinusoidal with no DC. Here it's not sinusoidal, and also there is DC. So the information is not very accurate, but that's the best we have. So we just assume that this is sort of sinusoidal, and therefore the losses will be a function of this perturbation. In a sinusoidal excitation without DC, this peak, of course, is B max. So when they say here B max, they mean this value, but for no DC. So this is in fact B peak. Okay? So what this curve shows is this figure of merit. The reason for this figure of merit is as follows. Let's just have a look at our equation, the one that we have just developed. We see here that we have L over B max, and there are some other parameters which are related to the design. Now L in a switch mode converter is proportional, the value of L, to 1 over frequency. The higher the frequency, the lower the inductance you need. Okay? So if you replace this L by, say, K over Fs, you get here this value. So this figure of merit actually is very important. It says that the larger this figure of merit is, the lower will be AP, meaning the volume or the size of the core will be smaller. So this is the reason for this figure of merit. Again, there is some confusion here as to B max and B peak. We have just to bear in mind that in the case of the data given by the manufacturer, there is no difference between these because they are talking about sinusoidal excitation with no DC, so B max and B hat or B peak are the same. So we see here, for example, that if we like to work at 100 kilohertz, then say this material 3C96 seems to be the optimal one. Bear in mind that this is actually it's a 2013 data sheet, so therefore there are some newer material, so this is just an example here. Also, we have to bear in mind that this is given for 100 degrees centigrade. Now the losses are a function of temperature. In fact, in many ferrites, the lower the temperature, the higher the losses. That is, you have lower losses at high temperature, meaning that it's better to run the core at high temperature because the losses are lower. So you do have later on to look up the relationship between the temperature and the loss of a given material that you are choosing. I'm not going into it in this presentation. Another point to bear in mind that this chart is given for a given power loss of the core. In this case, it will be 500 milliwatt per centimeter cube. This is fairly high. This is probably okay for flat magnetics, but for conventional like E-core, this might be a little bit too high. So again, this is just an indication, just the first impression of the material and how to choose them, and then later on we go into iteration and we look at the losses of the detailed losses of the material that we are considering. So here is an example. This is like a 3C96, and this is again 400 degrees centigrade. There is data of the losses as a function of temperature. I'm not discussing this here. Now this curve here is a little bit different. We have here now already the loss, the core loss in values of kilowatt per meter cube. And usually it's easier to comprehend this milliwatt per centimeter cube. And these are frequency lines. This is for 20 kilohertz, 100 kilohertz, etc. And this is this B hat. This is this amplitude of the excitation. Again, if we have a case like this, for example, it's a borderline type of an operation, and we have the B starting from 0 to a given value, etc. We have, on the one hand, we have B max. This is the B max in the equation that we had here. This is the B max. On the other hand, we have this B hat, which is the AC excitation, and I'm assuming that this is like sinusoidal, and this is what is given here, because again, the losses are due to this excitation. Everything is approximate because we don't have good data of the effect of the DC on the losses. So the best we can do is the data that we have for 0 DC. So in this case, this is B maximum that will plug into the area product equation, but this is the peak value here that will determine the losses. So if, say, I'm running at 100 kilohertz, and say I'll set up, say, 200 milliwatts per centimeter cube as my limit, then I end up with a B hat or B peak of 100 millitesla, meaning that B max that I'm going to put in this area product equation is going to be 300 millitesla. So once I do the calculation, now I know everything. This is from the electronic design. This I've just discussed. I can calculate this. Then I go to datasheets, and I'm looking for a core that has an AP which is either equal or, better yet, a little bit higher than this AP that I've calculated. Now in the core, the data of the cores, we do have the effective area. That's a cross-section area. Here it is, for example, 80 millimeters square. This is this cross-section area here. This is this plus this, or this area here. And also from the bobbin, we have here the winding area, which zooming it here, given here, and in many cases the vendors are actually giving already the product, the area product, the cross-section area of the core times the winding area, and in this particular case it's 8,980 millimeter to the fourth, because in area times area. Now if this number is not given, then if I have this number for the winding area and I have this cross-section area, I can just multiply the two and get the number, which is of course the same number. Now again, one has to be extremely careful. This is in millimeter to the fourth, and we are working in meters, so it has to be adjusted to the right units. Once I choose the core, I can go back to this equation that I had before and calculate the number of turns are needed for the primary. I know everything here now. And then for the secondary or any other winding, according to the turns ratio that I know from the electronic design. So this takes care of the number of turns. And of course, the size of the wire is a function of the current density that I've decided on. And then I need a gap. If this is a core with an air gap, I need to determine the size of the gap, and there are two ways to do it. One is to actually build the unit and then put spacers until you get the right inductance that you need. And this will be determining the gap experimentally. Now you can estimate the gap by this equation because you can calculate the mu that you need. This is now, everything here is given. This is the inductance, this is the magnetic path length, and square AE is the cross-section area of the core. And from here you have mu, and then you can calculate what is the required relative permeability, and then approximately the relative permeability is equal to the length, magnetic length here, over Lg, the gap length, and from which you can calculate the gap length. So, wrapping it up, in order to get the core that you need, you have to calculate AP, part from the electronic design, part from power loss consideration. You choose the core from the datasheet. You need an AP which is sort of larger than the one that you've calculated. You calculate the number of turns, and then you either calculate or experimentally determine the gap until you get the required inductance. Now, obviously, in a design, you may need to iterate because you can calculate the losses once you have the design and see if they are knowing the resistance of the wire, and then decide whether it's okay or maybe you'd like to adjust a little bit the design. So let's have a look now at a comparison between a flat magnetic element and, say, this is an ETD type core. I'm showing it here in a horizontal mounting, but it could be also vertical. There are two versions of bobbins that you can get. Here, it'll be either a printed circuit board that you have the two parts here of the core clamped across it, or this could be a standalone unit having small PCB boards here which are interconnected, and then this is clamped together. Now I've chosen two cores with the same area product value. The first one is an ETD29. It's a cross-section area of the core of 78 millimeters square, and the winding area 90. And the area product is 7,000, approximately 7,000. And then I have another core, and that's the flat magnetics. It is, of course, the height is shorter than the ETD core. And again, I've chosen it in such a way that we'll have the same area product. In this case, the cross-section area is 130 millimeters square, and then looking at this window here, the two halves, I can find out the width and the height, and the product of this is the winding area. And then when I multiply the cross-section area by the winding area, I get this number, which is the same thing as the ETD that I've chosen. So these are core of comparable size in terms of the area product. Now, when I compare these, first of all, I have to take into account that the actual winding of the PCB needed for the flat magnetics is extending beyond the core, because if this is like here's the winding, of course it has to be, you have to have enough space here in order to have these wires going around and back here and then again here. So this is in fact the PCB that you need for this core. It's extending. So if we look at the, say, footprint in this case, and I found that this is the footprint for the flat magnetics, and for the horizontal mounting mounted ETD, I found that it's about the same. So as far as the height, however, here we have 28 millimeters for the horizontally mounted ETD. Obviously it will be much, much higher if it will be vertically mounted. And here it's only 6.4 millimeters. This is about 3 millimeters. So this is much, much shorter than this one. And therefore, we see here the advantage of the low profile feature of the flat or planar magnetics. Now, in the case of the ETD, we found that the cross-section area is 76 and in the case of the flat core, planar core, it's 130. That's not surprising because the winding area here is larger and here it's smaller, while the product is the same. So this is twice here, which means that we need half the number of turns in this flat magnetic, which is one of the features of the planar magnetic element. So we understand that we're going to have a lower number of turns, and therefore the losses will be lower if we use the same current density, or we can increase the current density to get a same power loss. So because of the smaller filling factor, it would seem that we need a larger area here, a larger winding area, in order to accommodate the number of turns, because we are not filling the window that well. But since we can use J, that is the current density in the flat magnetic, to be larger than this, then so K is smaller, but J is larger, and B max can actually be larger because we can dissipate more of the loss of the core. So therefore, all in all, this term becomes larger, and this is why in the real design that we have seen here, the real winding area of the flat magnetics is half of that of the ETD. So this brings me to the end of this presentation. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.